Hey everybody, and welcome to another Jamovi tutorial. In this tutorial, we're going to explore another fantastic add-on module that you can add to your base Jamovi to help you with your teaching. This is called the Central Limit Theorem demonstration module, and I'll explain how you add that to your Jamovi. But first, just as a reminder to everyone who watches my videos, especially out of order, even though I episode them and all that stuff, I just want to make it painfully clear that we are now playing with Jamovi version 1.8.2 as of recording. In this tutorial, we actually don't need to open any data. So what you do is you just go up to modules, you go up to manage installed, and I'm going to have this installed on my stuff already, but we are looking for CLT. There it is, CLT demonstrations by Gasper Kankar. Thank you, Gasper. Simple simulations help students visualize first lessons in probability, how and binomial distribution approximates normal, and how law of big numbers or law of large numbers and central limit theorem work. Students can visualize correlations on different sizes and grasp important concepts when testing hypotheses. So if you're using Jamovi in your teaching, you can then have your students download it because it's free. You can have your students download it, and then they can do homework assignments on probability by using Jamovi in this case. Now, once you've added the module, it will be on this bar, and you'll find it under demonstrations. Apologies, Snow Cluster, Med Decide, it all groups together. But we're looking for demonstrations, and we have 3 Central Limit Theorem modules, and we'll go through each of them fairly quickly. You can do correlations as well. You can show what happens to correlations when you change a couple of parameters, and then you can do the testing hypothesis module. These do not require any data. So you can just, when you open them, they're just teaching modules. You change parameters and the output will change according to the parameters. So let's talk about tossing a coin first. Okay, so it brings up the results and it brings up the input modules panel here. And so we have 3 parameters that we are going to do. By default, it's going to be 1,000, n of 20, so number of coins that we have, and then the probability of success, which is 0.5 on a fair coin. Now, you can change that value in case you want to show what happens when it's not a fair coin. So if it's like a loaded coin or something like that, just to make sure that your students, when they're cornered by gambling addicts in a dark alley somewhere, that they'll know how to make decisions with an unfair coin. I don't know why you would change the effect that there is an unfair coin, but that's what we'll do. And so with this default setup, 1,000, n of 20, and a fair coin of 0.5, the output will automatically show you the binomial distribution and the normal distribution of this. So let's see what happens if we change this to an n of 100. Now, this is a drop-down menu. You don't get to choose what n's you have. And so this is, a basic setup. But let's change it to n200, and you can clearly see that with a fair coin and 1,000 flips, that the binomial distribution and the normal distribution are essentially the same. But if we go back to n of 3, you can see that the binomial distribution is slightly different than the normal distribution. There's a tail to the binomial distribution. Now, if we change this to an unfair coin and say 0.75 is the probability of success, you can see that it shifts, and you no longer have a normal distribution. You have this tail down at the bottom. And if we change that to n200, but it still approaches normal distribution. And so that's what the central limit theorem is trying to tell you, that if you're not even doing, if we put in 50,000 here, which is the maximum, my computer's working, you can see that the binomial distribution and the normal distribution do tend to overlap, but you end up getting this tail because we have a weighted coin here. If we make that a 0.25, you can see that the tail will shift to the other side, but not as stark, which is very cool. So that's how you can show what happens when you change various parameters of tossing a coin. And if we do 50,000 and point back to a fair coin of number of coins n being 200, look at that. If we just had 3 coins, it's a normal distribution around 1.5, which is pretty cool. All right, so that's tossing a coin. Let's change now to throwing dice, which is far more complicated than tossing coins because we have multiple outcomes. So here's where you have full control over everything. You don't have a drop-down menu. So you can do number of trials, one between 10,000 defaults to 1,000. You can have you can change the number of dice between 1 die and 6 dice. By default, it's 3. And then number of sides on any single die would be anywhere from 2 to 10. So you could have a 2-sided die. A 2-sided die is a coin, to be honest with you. And so that would be 6. So here we have 1,000 trials, 3 dice, 6-sided. Your standard 6-sided cubic dice, right? And you can see here that the instead of a binomial distribution versus a normal distribution, we have the expected value versus the normal distribution. So the expected value would be the value that we would expect to see with these 3 parameters, and we can change the value of these where we can get an expected normal distribution by changing the amount of trials that we have. So if we change that to 10,000, look how much closer the values get to normal on the expected. And then if we change this to 10 10-sided dice, the blue line is becoming less clunky and more normally distributed. Can't say things. And so if we change that to 6, what happens to the distribution? So it's doing all of that calculation. And here we have a almost normal distribution of expected values between what the sum of the dice would be. Would it be down? So we have 6-sided die, 10. So 2, 3, 4, 5, 6, 7, 8, 9, 10. How many times? And we can get up to a value of 60, right? So the event space includes a million. So if we change that back to 1, and we have 1 dice, and we have 2 sides, the expected value would be somewhere between 1 and 2, but we rolled it, and we ended up only getting 1, right? So number of trials, we just flip this coin once. You either land on a 1 or you land on a 2. And so the average of that would be 1.5, of course. And so that's where you see this curve. And then we can show students what happens when we flip it more times. So if we change this to 100, what happens? Well, again, the average is going to be 1.5, and we've changed that. So now if we do 500, it's still looking normal, but the expected value is going to be either 1 or 2. If we change this to 1500, right, we can see that changing. And if we change it all the way to 10,000, we get 2 essentially equal bars. So that's the throwing dice. And then if you want to cap it off with just a Central Limit Theorem idea here, you get a sampling table where you would get sample size. So we can change our sample size between 1 and 200. We can change our number of trials between 1 and 5,000, and we can get either a normal distribution, a uniform, geometric, log normal, or binomial, which you would then describe how many more numbers do we need in a particular distribution to achieve that kind of shape. Okay, so if we change this to binomial, you can see that the distribution still does look normal. Log normal, again, would look like this. Geometric would have a sort of parabolic shape to it, just like a normal distribution. A uniform distribution would show you what it would look like here. But if we change this to 200, you can see that the distribution is still uniform. If we change this to normal, and then these would all change. Number of trials, if we put this up to 5,000, the bar itself is going to change, but you can see that, look at that, it's essentially around 0. And you can get the number of samples, the mean of that sample, this is essentially 0, negative 9.73 to the 10 to the negative 4th. So this is 0.001, basically negative 0.001. The standard deviation of all of the means, and then the standard error. And this is what it looks like at a closer level. Okay, and so that's the central limit theorem. You can explain to your students how that works. A couple of other demonstrations that they've included in this module include correlations, where you can change the value of the pairs that we have, and whether or not the correlation is in between -1 and +1. So if we start this at 10, and what happens to that? So we have 10 data points around here, and what it would look like if it was a 0.7. If it was a 0.7 correlation, if we did -0.7, click out of that and can show you what that looks like. But if we put in 2,500, what that would look like at -7 or 0.95, what that would look like. Look at that. That's beautiful. 0.3. What would happen with the dots? Well, you can see that the cluster gets wider. And one of the things that I tend to do with values that you see in psychology quite a bit is I'll draw ovals around these. And when you see an oval that's large, okay, how do you determine where that line goes? Just by looking at it. And it's really hard to see when you have that many data points, 5,000 data points for something that's 0.25. But if I change this to 0.95, look how close those values get to that line. So it's much easier to determine where the line goes on this ellipse as you draw an oval around it, where the center point of that oval goes, as opposed to 0.25, right? Where it's just like, oh boy, where's the central point of that oval? And you can use annotation tools and draw on that if you've got the functionality. And the last demonstration for this video, because it is going a little bit long, is the testing hypothesis. And so you get confidence intervals and a summary table, and you can change your population difference, so 0 through 10, with a standard deviation set at 10, sample size 5, between 500, number of trials, and the p-value for, this should actually say alpha for the type 1 error probability. We're going to use 0.05. And so you can change the population difference. Let's say it's 3, and we have a sample size of 50, and number of trials. Honestly, number of trials, let's just say it is 1. Okay, so if you were only to do it one time, If you were only to do it one time, you have a population difference, so a mean difference of 3 with a standard deviation of 10. With 50 people, what are we going to see? And so you get the expected difference is 3. The average distance is 2.85, which is the expected difference is 3 here, and the average difference in mean is this 0.25. Sample size is 50, and so this is your or your confidence interval bar, okay, number of trials. The probability would be 0.001, critical, and that's the critical P is 0.005, and so looks like we could change that. But if we change this to like, let's do 50 trials of this, and so this represents our hypothesis testing. So if we had 1 sample of 50, 2 samples of 50, 3 samples of 50, 4 samples of 50, 5 samples, so on and so on and so on. And then here we find what gets marked as red as some of these samples that go through this process. This one isn't looking so hot. This one's actually in the opposite direction. So, 1 out of 50 trials, we're going to end up with a confidence interval that does not give us our expected difference. So the average difference in mean is the average of all of these means to this blue bar. And it looks like that the probability of getting something like this out of 50 is 0.02. So hypothesis testing, that would be a place to reject the null hypothesis. So that is the demonstrations, the CLT, the Central Limit Theorem module in Jamovi. If you like this video, consider leaving a like. If you like this content, please consider subscribing for more of these kinds of tutorials, including tech tutorials, psychology content, VODs, all of that kind of stuff. It would be awesome if you did. Thank you so much for watching.